Lesson 11, first law of thermodynamics. We will be able to explain and use the first law of thermodynamics. So our goal today, and I would like you to write this down if you haven't, is to try and explain and use the first law of thermodynamics. Now, we've already discussed the first law of thermodynamics. We've talked about it. But today's lesson is going more than just talking about it. Today's lesson, what we want to get to, is we want to get to a point where we can say, okay, how can we use this law? How can we use this law to do, believe it or not, calculations? Because the law that I taught you guys yesterday about the first law of thermodynamics is just like a quick, answer that you would give to someone in year 8, year 9 about what are the laws of thermodynamics. In year 11, we're going to start using these laws to actually calculate things. Let's go back a few slides to see what we talked about last lesson. So last lesson, what we talked about was we discussed the laws of thermodynamics. We talked about the first two laws. The first thing we talked about was thermal equilibrium. Thermal equilibrium means two objects that are touching are the same temperature. So when you start off with something, when you start off with two objects, you might start off with a really, really hot object and a really, really cold object. And then over time, they will turn into two objects of the same rough temperature. And that is when they're at thermal equilibrium, when they're the same temperature. If you put if you cook dinner and you put it in the fridge and it's warm when it goes in the fridge, but then eventually cools down to the same temperature of the fridge, that's because it's reached thermal equilibrium. It's not going to get colder. Equilibrium has the word equal in it because equilibrium means equal. So thermally equal essentially is what that word means. The 0th law of thermodynamics just says that if two objects are in thermal equilibrium with one object in common, then those two objects are also in thermal equilibrium. I hated this explanation, so I much prefer this one. It said if the paper and the scissors are the same temperature, these two are in thermal equilibrium, and these two are in thermal equilibrium, then therefore these two must be in thermal equilibrium. I sort of said to you guys, the answer is might be a bit duh. Obviously, if this is 25 degrees and if this is 25 degrees and this is 25 degrees, then obviously this will also be 25 degrees because they're all linked together. So that's all that law is saying. The first law, though, is a bit more complicated. It says that energy is conserved and cannot be created or destroyed. All energy must be accounted for. Now, whenever I give students a question like this, they always remember energy can't be created or destroyed. If I ask a student during revision, that's what they'll say. But really, the idea of conservation and accounting for is far more important. Now, how do we account for that energy? Well, we know that energy exists in a system according to the internal energy. That internal energy can be affected by work and by heat transfer. We've talked about heat transfer already. Conduction, convection, radiation. But we hadn't talked about work. So I briefly introduced you to work. Work is another way that energy can change in a system. Work is when a system or something pushes against something. It might push against air. It might push against a paper bag in this case. It might push against a piston. It might push against it might push against a plastic balloon. If it's pushing against something, then it's doing work on something, and it will lose energy as it pushes. Just like how if I asked you guys to push a rock up a hill, you would lose energy. You get tired out as you pushed it up the hill. That's the same idea, except in this case, the thing that's pushing is actually just some non-living thing. So now we're going to combine those ideas together to create a formula. And that formula is going to be a formula that we're going to use for a bunch of calculations. So we're going to take our time to get there. The part that makes this formula that I'm going to show you difficult to understand is when something is positive and when something is negative. So to do that, I'm going to go through this slowly. And the only way to teach you guys whether something is positive or something is negative is to get you to understand the concepts. So first, let's talk about the vocabulary. The vocabulary we're going to use is I've already been using this vocabulary, which is not very fair that I haven't actually talked to you guys about these words. Is I'm going to start off with the first bit of vocabulary, which is, hush now, lie down in the bed, go back to sleep. A system. Now I keep reusing this word, a system, and most of you guys have not questioned me, so I'm going to assume that most of you guys sort of understand what it means. But just so we know, a system is a part of the universe selected for study. Okay, so a system can be something as big as a planet. Okay, and we could talk about a system can be something as big as a planet, or it can be something as small as a test tube. Both of these can be used as things that are a system, and they're just part of the universe. The surroundings, and I'm going to use this word a lot too, are the immediate environment around the system. So the surroundings around a planet, of course, just the stars. The surroundings around a test tube might be the room that it's in. If I've got a can of soft drink and it's inside the fridge, then the surroundings are the fridge, whereas the can of soft drink would be a system. Okay, a system is just a name that we give to the thing that we're looking at. Now, there are three types of systems that we're going to be talking about. The first type of system is called an open system. An open system is a system that allows matter and energy to enter it. Okay, an example would be a coffee mug. I've actually got a coffee mug here. You guys can't see it because I've got the screen shared. Now, a coffee mug, why is a coffee mug a system? Because if you think about a coffee mug, the thing about a coffee mug is that energy can get out of it and into it. That means that as you put your hand up onto the coffee, you can actually feel the warmth coming out of the coffee mug. Also, matter can get into it. Oxygen molecules and other molecules can get in and out of this mug. And that can be bad if you think about it. If you're thinking about it, you think about, okay, well, for this coffee mug, it's like, well, that could mean that convection can occur, right? That coffee can heat up the air and the air can get less dense and then rise up and take heat away from the coffee. So convection can occur. You can also get conduction because of the heat going through the sides of the walls of the coffee mug. That's called an open system. Pretty much anything can happen. After the open system, we have a closed system. Whoops, I'll rub this out now. It's blocking my part. A closed system is very similar to an open system. A closed system is a system that allows energy in or out, but not matter. An example, this one is like a takeaway coffee mug. So if you think about a takeaway coffee cup, like sort of like this one, something you might get from Starbucks. Let me try and draw this again. What the difference between this and the mug is this thing has a lid. So yeah, sure, if you put your hand next to it, you can feel the heat come out of it, but no air can get in. It's trapped, right? There's no way that you can get air into this system. So therefore we say it's closed, okay? I might even draw some air. The air can't get in, so it goes around. The last type of system is called an isolated system. No matter or energy in or out. Okay, and the example of this would be a thermos, which is full of coffee because, you know, hashtag coffee love. So a thermos looks like this. If you don't know what a thermos looks like, thermos, I'm going to do a really bad job of a thermos. Actually, that's a pretty good thermos. A thermos has the liquid on the inside, so it would look like this. But heat can't get out. If you grab a thermos, it'll feel cold to the touch. That's because heat can't get out. And obviously, air and coffee can't get out either because it's sealed. So it's not just a closed system; it's like a super closed system, which is why we call this an isolated system. So these are the three ways in which, and I like this. This is intentional to refer to all of these in like with coffee because I want you guys to when you, because it's sort of just then it's like you can think of, okay, am I talking about a coffee mug? Am I talking about a takeaway coffee cup? Or am I talking about a thermos? So on the right here, I've got another picture of the same thing that I just drew. So the far left, I've got the open system. We've got the open system here. The open system, which is the coffee mug, you can see that O2 can get in and heat can get in and out. So I probably made a mistake when I wrote this slide. I should have said open system allows matter and energy to enter it. So it probably should be enter/exit, but still. So I don't want you to think, oh, well, it can only get in. And the closed system allows energy in, but not matter. It also allows energy out. So it should be in/out, but still, whatever, not that important. An isolated system has no energy in or out. So here's the middle one, the closed system. So energy can get in and out, but if you look, matter can't get in. Nothing can get into this thing. In an isolated system, nothing gets in, nothing gets out. So that's our first bit of vocab. Are there any questions on this bit of vocab here? Keep in mind, if you wanted me to go over it again, you can just write a secret message to me in chat. A private message, I mean. All right, I'm going to change the slide. Is that okay with everyone?
Yep.
Cool. I'm going to take that one yep as an answer that you guys are ready. So let's jump ahead now. This is just a picture. In case you didn't know, so on the left, we've got the coffee mug. This is the open system. On the right, we've got the takeaway coffee cup, which is the closed system. You can still feel heat coming through that cup, and heat can still get into that cup. So if it's a really hot day, you can still get into it. But, you know, you can't get air and stuff into it. And the last is a thermos, or a thermos. This thermos is open, but still, when it's closed, no heat can get in or out. That's why even though it's in the snow, you can still see that that coffee is quite warm. Actually, you can't see that coffee is quite warm. You have to trust me. Yeah. Okay. So here we go. Ladies and gents, we're going to explain the first law of thermodynamics in a different way. And this way that we're going to explain it is, and I'm going to go through this quite slowly because of it, but I want to try to explain it. Now remember, the first law of thermodynamics says that all energy must be accounted for. That means that we can account for all changes in internal energy. So what we're going to do is we're going to talk about it like this. A change in internal energy. Your system has had its internal energy change. Maybe it's gotten increased, which will mean the temperature goes up. Maybe it's gotten decreased, so maybe the temperature will go down. And what can cause that change in internal energy? Well, there are two things that can change that internal energy. The first, and I'm doing it in purple, if you look over here, I've got over here a what's going to represent a closed system. And the first is I've got this purple line here, which represents heat transfer into the system. And that's because this is the system and heat energy is going into it from the flame. I'm going to use purple to represent the heat, but that's what's going on here. Heat is being transferred into the system from the flame. Why is heat being transferred into the system? Because this is hot and this is cool. So therefore, we know from our laws of thermodynamics that energy always moves from the hotter object to the colder object. What's another thing that could happen here? Well, the other thing that could happen here is we could, let's just say this can of, let's call this a can of soft drink, let's call this a can of beans, I don't really care what it is. Let's say we really heat this can of beans up. What could happen is that it's going to build up pressure, because we talked about this in our second lesson that we ever had. You heat something up, the particles move around more. Now, if you heat up a can and it builds up pressure, ladies and gents, can I get someone in the chat to tell me what's going to happen if I heat up a closed can on a fire? What's going to happen to the can? Someone in chat or out loud, tell me. Explosion, kaboom. Okay, but not as quite as, we're not going to go that violent. Yeah, you're right, but we're going to still tick to that idea. As the pressure builds up, what's going to happen is that the sides of our container are going to bulge out, because the liquid is going to push against the sides of the container. It's going to move them over a distance. That, in green, is the work done by the system. So, and you'll notice here, ladies and gents, that I've actually used, and I've used green to represent that. So the green, in this case, represents the work. And so now what I want you guys to look at is I want you to spend some time looking at the signs. So if you think about the internal energy of the beans or whatever it is, okay? Heat transfers into the system, that's going to increase its energy because you're putting energy in. Okay, you're going to be adding energy into the system. And that's why I've underlined that word into, because we're putting energy into the system. But when that system does work, when that system pushes out onto the sides of the can, we say that the system, it's doing work. And so that means we need to remove that. We need to subtract that. If we put in 20 joules of heat energy, and these are the type of calculations we're going to do. We put in 20 joules of heat energy, but then we push the walls of the can out with 20 joules of work. So it takes, maybe we push that out, and that's 20 joules of work. And that means that our change in internal energy is 0. So therefore, we don't actually, the system doesn't heat up, because all the energy that went in got pushed out by pushing the cans out, the side of the walls out. So what I'm going to do now is I'm going to turn all of these terms into their own symbols. So these are the symbols. The change of internal energy, that is written down as delta U. Change in is represented by the delta, and the U is the internal energy. Remember, we've studied internal energy. This is not a new concept. Internal energy is the amount of energy that's connected to movement. It's all that energy got to do with kinetic motion, of translational motion, of rotational, vibrational. That's all that stuff is. Q, well, Q is our heat. That's our conduction, our convection, and our radiation. And W, well, that's our work. That's how much work we're pushing. So the idea is that the amount of energy in a system, the amount of energy inside this cans of beans is equal to the amount of energy that goes in because of heat minus the amount of energy that that system is doing. If it's doing something, then it's going to lose energy. If you're pushing a rock up a hill, you're losing energy. If you're pushing the sides of a can outwards, then you're doing energy, you're doing work, you're losing energy because you're pushing against something. And so therefore your internal energy goes down. This is Newton's, I keep saying Newton, I'm sorry, because I'm so used to teaching motion. This is the first law of thermodynamics written as a formula. This is the formula that we're going to spend the rest of this double period fully understanding so that we can do questions on this stuff. I want to be able to give you a scenario and you to be telling me, oh yeah, well, that's going to have an increase in internal energy because the heat is, and the work is going out of the system at a lower rate than heat is going into it. I'm going to keep this slide up for a little bit longer, and I'm going to ask, are there any questions? Are there any queries? Is there anyone that's confused about what this means? Sometimes I actually just think of delta U as well. And I know this is cheating, but still, sometimes I think of delta U with just being temperature. That's obviously not correct. You can increase the internal energy of something without increasing the temperature. You can do that by getting the particles to vibrate more, and so therefore that doesn't increase the temperature. But honestly, most of the time, if you increase the internal energy, the temperature will usually go up. So that's how I usually think about it. Okay. So I'm going to move on unless anyone tells me to stop. All right. Jumping ahead. So here's that formula we just had on the previous slide. Delta U is a change in internal energy. Q is the heat added. Work is the work done by the system. So, and the key words here are to and by. So I always want you guys to think about it from the system's perspective, okay? So if the system is getting heat put into it, then it's going to be, that's one thing. If the system is doing work, then it's going to reduce the amount of energy. And so this is just the same stuff as the previous one. I do want to point out that all of these are measured in joules. Okay, so the first thing I wanted to show you guys is the two signs of Q. So Q is positive. When is Q positive? Q is positive if the system absorbs heat. For example, if energy from the sun, then Q is greater than 0. Can you guys give me, just so I can test you guys in chat or out loud, it's up to you guys, why don't you give me another example of something absorbing heat? What's another example of something absorbing heat? So I've done one here. If a system absorbs heat from the sun, black clothes, yep, no, that's not what I'm talking about. I want to know what's an example So I've done one example, which is energy from the sun heating up something. What's another way energy can enter a system? Radiation, yeah, sure, but I want like a physical story. I can give you an example. When you put a campfire, battery, both of those are good. Solar panel, campfire is a good one. I'm going to stick with Minvu's answer, campfire. Campfire, heat goes from the fire into another object. What's another one? Solar panels, yeah, but solar panels is also, David, just another example of light. I want nuclear power plant. That's more got to do with nuclear power. Torch, yeah, sure, torch might work. Anywhere where heat goes into a system. So I'm talking about, when I'm talking about this, I'm talking about a microwave. I'm talking about a stove. I'm talking about an oven. I'm talking about like a heater, anything that's warm that will heat something up that energy can go into it. That's what I'm talking about. So that's when energy goes into a system. When energy goes into a system, then Q will be positive. However, what will make Q negative? Q will be negative if energy leaves a system. If a system releases or loses heat, then your Q will be negative. Like, for example, when you sweat. When you sweat, energy comes out of you, and therefore your Q is negative. Your Q is less than 0. Another example that I can think of something that's Q is if you put, something in the fridge. If you put something in the fridge is cooler, so the heat will leave that object and go into the fridge because it's cooler in the fridge. So that would be something very negative. Any sort of system where you're losing energy, that's going to be when the Q is negative. So I just want you guys to start off with to get this idea, okay? Q is positive, something is heating it up. Q is negative, it's getting cooled down. Why is it getting cooled down? Probably because its surroundings are colder, or maybe because it's been putting. A fridge in the desert without power would not work very well. So, yeah. Are there any questions about the signs of Q? So let's go back over this again. When Q is positive, energy is going into it, okay? It's a cold object that's getting heated up, whether it be by the sun, by a campfire, by an oven, by a microwave, anything that's by an explosion, anything that's heating that up. When Q is negative, we're talking about something where heat is leaving an object. So maybe that object is being put in the snow, in the ice, in a fridge, in the deep outreaches of space. Is it possible for Q to be neutral? Yes. Q would be neutral if there was no heat going into or out of the system. So that would be an isolated system. In an isolated system, there is no change in Q. Q is 0. Okay. What about work? Now, work is a little bit more complicated, but we're going to talk about it. Work is positive. If the system does work on the surroundings, then it is positive. E.g., balloon expands, W is greater than 0. Now, I want you to be careful with this idea. When I say work is positive, that means that, and I'm going to draw this very carefully, that means that the W is positive, okay? So if I subtract a positive, it becomes subtraction, okay? So remember I said that if a system's doing work, then it's losing energy. So if it's doing work and this number is positive and you subtract the positive number, it's going to make this number less. So, for example, when a balloon expands, then it's doing work on its surroundings. If you've got a piston in a car engine and that's pushing that piston upwards, that's doing work on the system. If you've got a balloon, not a balloon, we'll go with the can again. If we've got a can of beans and then it gets expanded out, then that is called, it doing work on its surroundings. I'm giving you guys the examples this time because sometimes coming up with examples of things that are pushing on the surroundings are a little bit hard to think of. I think there might be an example about elastic bands here, but I can't recall. So I'm just going to leave that at the moment. Okay. What about when work is negative? And this is probably the most confusing out of all the answers. If the surroundings do work on the system, so notice the reversal here. The system does work on the surroundings, where here it's the surroundings do work on the system, then work will be negative. So for example, pumping up a tire, then W will be -0, will be less than 0, because you are putting work into a system. If you've got a can and you instead decide to crush that can, you are doing work on the system. Okay? The idea is, and this is where it's going to get confusing, is that if you've got delta U equals Q minus -W, because you're doing work on the system. If you're doing work on the system, you're putting work into the system. That's going to mean that your energy is going to be the heat put into the system plus the work you've done on the system. That's why you've got to be careful with this negative. So when you do work on a system, and that's why I suggest always doing brackets, that work gets added to the total amount of work. Now, this is going to be a bit confusing at the moment. I know some of you guys are going to be like, what? But it'll help a little bit more when we do examples. But if you want to take what you want the takeaway to be at the moment is make sure you use brackets when you do this formula. And remember to ask, am I doing something to the system? Am I forcing air into the system? Am I squashing the system with a piston? Or is the system doing work? Is the system expanding? Is the system pushing out against it? Is it an explosion where the system is pushing air away from it? What type of system is going on here? Okay, so before I do that, are there any questions about this so far? Any queries? Anyone confused? When is W negative? When is Q negative? So on and so forth. Is anyone confused about W being negative, or are we all okay? Could you quickly re-explain this? Okay, really quickly. Okay, Q is the easy one. Where Q is positive, heat is going into something. It's like heating something up. Heat is going into the system. Yeah, I know you're probably saying, no, just the work stuff. Yeah, I know, but I will, don't worry. Q is negative, energy is leaving something. Heat is leaving something. It's going from a hot object, like your hot body, to the cool air around you. Work is when can be positive or negative. When work is positive, that's when the system is pushing against the outside world. When work is negative, it's when the outside world is pushing on the system. So this one is like, when work is positive, That's when you're out, where you're pushing against the outside world. When work is negative, it's like when you are pushing into an object, into a system. Okay. The idea is that when you're pushing out, you are losing energy. So therefore, negative subtracting a positive will make it a negative. You will lose energy. But when you're pushing work, when you're pushing into a system, it's negative subtracting negative, which means positive. You're increasing the amount of energy on the system. You're increasing the amount of energy, so you gain energy because you are pushing into it. There's a really cool little demonstration that I do, which I will show you guys tomorrow if we're at school, where you can actually get something to ignite, to actually catch fire without using any heat whatsoever. All you do is you do a large amount of work on something. And that you really, really squish something down. You guys might have seen like those hydraulic pressure kind of things where they squash things and they get really, really hot. And that's because as you squash something, you're adding work to the system. There are a lot of examples I'm going to do, but I'm going to move on for now. I'm going to come back. So why did these, someone just asked one more question, but I jumped ahead anyway. Can the internal energy be negative? Is a question from the, yes, you can lose energy. So the change can be negative. And that will usually mean that you've gotten colder. And that can be caused by a couple of things. It could mean the reason that you get colder is, I'll go back a sec. The reason you can get colder is because maybe you've lost energy from the system in the form of heat, maybe because you've put it in a fridge. Another way you can lose energy is if you have done a lot of work. So if you push that balloon and you increase it, you might lose so much energy that the air inside that balloon might cool down. Why do we care about these? Why were these invented in the first place? These laws of thermodynamics were really important because of the Industrial Revolution. Now, I know that you guys have studied the Industrial Revolution. I'm not sure if you studied in year 9 or year 10, but yeah, if you want to tell me in chat, I'd appreciate that. But the Industrial Revolution, for those of you that don't remember, was essentially when human labor was replaced by these beautiful things we've got around in this picture, which is, of course, machines. All these machines are being powered by, it looks like this top rail, which is going to be a turning motor. And that turning motor, the thing that turns, what they were using was a steam engine. The steam engine, and you don't need to memorize this actually, I've just put this up here. A steam engine was a way that they could convert high pressure steam into work, which can move a piston. And the reason that they really cared about this is because then suddenly you could actually get, you could get a large amount of things working. You could get a large engine moving. You could get a large wheel spinning, which meant that humans didn't have to do it by hand. You could use a steam engine. And then, of course, this allowed them to make trains, which allowed them to move large amounts of things. So the steam engine was really important. And understanding how this steam engine worked was how the first law of thermodynamics was created. So the first law was created to understand steam engines. I like to just show students this because and this is where this type of science exists in history. And I like to show students this because science is not by itself its own little thing, its own little like, when I talk about science, I know that I'm talking about laws, but these laws were invented in specific times. You guys have spent a lot of time talking about the Industrial Revolution, talking about the rights of people and that sort of thing. Well, this is the science that was going on. How can we understand these machines so we can make them better? So, by the way, it's just a quick little thing so you can see what's happening here. When this goes red, I can't pause it because unfortunately that would require a lot of. When it goes red, so now it's filling up with steam, and that steam is pushing that piston. It's doing work on the system, and then it pushes the cool gas out when that piston goes back down, and then new hot gas goes in. And we all know that hot gas, hot steam expands because it takes up more space because it's less dense. And that's going to push that piston. The steam engine converts high pressure steam into work. So we're already converting steam or temperature into work. And that's the reason why we care about this law. Because ultimately, what this law says is it's got temperature and it's got work. And usually when something cools down, it just cools down slowly. But we want to say, is there a way we can get this to cool down, but to cool down by moving something? Can we harness the energy that is the heat? Because it's really easy to heat something up. It's really hard to take that heat energy and use it for something. And that's what the steam engine did, is it turned that temperature, that heat, that steam that was easy to make into work. And ultimately, steam is cheaper than humans. And that's why the Industrial Revolution started, and that's why we have, that's what allowed humans to be able to, do more complicated tasks, because ultimately the steam engine can do the basic ones. So this is, I really like this slide and this picture here showing you guys steam engines. Like, if it wasn't for the steam engines, we wouldn't, this is, I believe, a textiles manufacturing, we wouldn't be able to get clothes for the masses as easily. We wouldn't be able to get engines, train engines, to move things around, to allow us to colonize new parts and connect people to cities and so on. My goal now is to talk to you guys about 4 examples, okay? 4 examples of changing of internal energy. And then what we're going to do is we're going to do some just number examples, and then I'm going to let you guys loosen some of the questions that I've got for this topic. So the first example is, I wanted to talk to you, and these have got some weird names. But the first example is called, these weird names you don't have to necessarily memorize, but I'm just going to show you them anyway. What we're going to talk about, the first weird name is called is constant volume. And the constant volume, the word that we use for that is isovolumetric. Iso meaning same, and volumetric meaning volume. Constant volume means that there is no change in volume. There is no change in the amount of stuff. And if there's no change in volume, then that would be, you can't if there's no change in volume, then we can't really get anything going on, okay? This would be a closed system. So actually, I'm not going to write that. I'm just going to write if there's no change volume. So an example of a constant volume, what that would mean is that the change in energy is only dependent on the heat. That's the only thing that can change the energy, is the heat. So an example for those are the heat pack and the cold pack. So the heat pack, it can only change energy by heating up your hands. even though that heat pack is gel, it doesn't expand. It just stays the same size. Same with the cold pack. The cold pack only changes its internal energy by getting warm. So its internal energy increases, right? But it doesn't expand or contract. Its volume doesn't change. Okay, so that's the first weird one, is when your change in work is zero. There is no change in work. Okay, so the only way to increase and decrease in energy is by, gaining or losing heat. I think this would be a closed system. The next one. So that's the first one, okay? Are there any questions about this one before I change the slide, which I didn't think was a different slide, but apparently it is. Nope. Okay. So we're going to do this. I'm going to put this back up here. Delta U equals just Q, because the W would get cancelled out in that first one. What about constant temperature? In this case, isothermal. Same, again, iso meaning same, and thermal, temperature. By the way, we're all in like isolation, which is the same location. Isosceles triangle is a triangle of the same side. So iso just means same. So what happens if you get something that's the same temperature? Delta U equals 0. Okay, with delta U equals 0, right? Let's do the maths here, right? If delta U equals 0, then that means that 0 equals Q minus W, which means that W equals Q. All of the work done in that system is caused by the heat that goes into that system. So what that means, where that comes up, is in car engines. Why? Because we want the energy that goes in, we want all of that heat that's being caused by the combustion, all of the heat that is caused by this combustion, we want that to go into moving the pistons. We don't want that heat coming out. We do not want that heat coming out. That's not what we want. We do not want this heat. We want just this energy, just the movement. And so that's what we get. Now, is a engine isothermal? No, it's not isothermal, because we know, if you guys have ever touched the top of the hood of a car after you've driven somewhere, it's going to be warm. But the more isothermal, the better. We want this to be as cold as possible, because we want all of the energy from the explosion going to just work. That's what isothermal means. Are there any questions about isothermal? So the next question is I guess, okay, so we've done one where there's the same volume, we've done one where there's the same temperature. What if we do one where there is, I think the next one would be, for my guess. So we've done one with that work, we've done one with that, and with that internal energy. I think the next one will be, what happens if no heat can get in or out of the system? No heat transfer. Now that's got a weird term. It's called adiabatic. So you can't use that ISO thing. So adiabatic. Do I know what adiabatic means? No, I don't know what it stands for. I can't do that same breaking it down. But adiabatic means Q equals 0. So let's see, if Q equals 0, then that would mean that delta U equals negative W. So the first one was delta U equals Q, which is all of the energy is just caused by all the energy, all the change in temperature just caused by heat leaving the system. This one says there's no change in temperature, so all of the heat goes to moving the object. This one says there is no, all of the change in energy is caused by work being done on the system or work being done by the system. So the example for that is usually the example we do is the atmosphere. That's a great example. Why? Because ultimately the atmosphere, we can assume that there's no heat entering the atmosphere. And you might be like, what do you mean there's no heat entering the atmosphere? You've got a dirty big sun right above you. It's like, yeah, I know, but generally we ignore that because like there's not much to absorb it because it's just like very, very sparse particles. So what that means is that as you go higher and higher up, there is less and less work being done by the particles because they take up, their volume increases, and so therefore their temperature goes down. That's really the hand wavy sort of example that I've got here. If you don't fully understand this bit, I don't really mind. But yeah, the idea is as you go, and this is, these systems are incredibly rare because heat usually will be absorbed or transferred by convection or something somehow. But still, the general idea is that as you do more work because you expand more, that's what this is, expansion. As you expand more by going up into higher and higher parts of the atmosphere, your temperature will go down. And that's because, yeah, there's less pressure higher up in the atmosphere. So you can expand more. And that allows you to get, that's because gravity is less. And that will make you get colder and colder and colder. The last of our 4 types is when Q is 0 and W is 0. That would mean if, so the first one, again, writing these down, delta U equals Q. This one, delta U equals negative W. This one, Q equals W. And this one, delta U equals 0. An isolated system. Now, an isolated system is just when you have a box that is shielded from the world. That means that no heat can get out. It can't do work on these walls because they're too stiff. So therefore, nothing changes. There is no change in energy. So, and it's very hard to get one of these types of systems. Because again, usually some form of work will happen. Usually some form of, something will happen. So let's go back over these. Isovolumetric means that no change, no work is done. So all of the energy is lost by heat. Adiabatic means no heat is transferred. So all of the energy is lost because of work being done. Isothermal means there's no change in internal energy. All of the work is turned into heat. And the last one is isolated, which means there's just no change in energy. Now, I'm going to upload this video later on. If you didn't quite understand these 4 bits and pieces, I suggest you watch them back. If there's one of these that you didn't quite understand, I'd suggest looking it up. I reckon you could very easily find a great explanation adiabatic on YouTube. If you're like, wow, Mr. Guru did a really bad job, I actually don't think I did a very good job of explaining adiabatic. I'm sure that there is some Khan Academy, Veritasium, bloody Vsauce video about adiabatic systems that I don't know about, that I haven't seen, and they probably do an amazing job of explaining it. They probably have animations and that kind of stuff. But I'm just going to I'd suggest do your own research. What we're going to finish this lesson off with is 2 examples, and then I'm going to let you guys loose on some of the questions. Right. So these examples are pretty dense with their with the information in them. So, but I'm going to. So if you guys want to copy them down, that's fine. If you don't, then that's okay. But we're going to start with the first one. But I'm going to give you guys a second if you want just to digest it, to read it first, and then what we'll do is we'll work on it. Okay. Now, I'm going to ask for your input here, ladies and gents. So I'm going to ask you guys to put some things in chat. So don't think that so that means the questions are about to come at you. So make sure that you have a look at this. So the first question is here. A balloon is placed in direct sunlight. Okay. The sunlight supplies 200 joules of energy to the balloon. The air inside the balloon, whoa, whoopsies. The air inside the balloon pushes out the balloon surface, doing 50 joules of work. By how much does the internal energy of the air inside change? Okay, to do this, we're going to break this question down into its parts. We're going to start with heat, which is Q. Can someone tell me in chat how much heat is transferred into the system? How much heat is transferred into the system? Privately, someone said it, which means is great. I can wait for someone to say it. Beautiful. Both the person who sent it to me privately and the person who sent it publicly got the answer correct. 200. But now I'm going to question you guys. Q equals 200. Now I'm going to question you guys. Is that positive 200 or negative 200? Dylan, both people, everyone's saying positive. You are correct. It is positive 200. Now the important, you might think, oh yeah, sir, like that's an easy part. That's actually crucial. We have to understand that energy is going into the system. Okay, the sunlight supplies to the balloon. The balloon's not getting cooler. It's not releasing energy. The energy is going into the balloon. So the next one is going to be W, work. Can someone tell me how much work is being done? And then for bonus points, can you tell me if it's negative or positive? Okay, I've got one answer. I've got one guess. For minutes is positive. Let me see if I can get some more ones. Yep. Okay, so the answer to this is positive 50. Let's work out why. Remember, when the object, let's go all the way back. Remember, when the object does work, if a system does work, then it is positive. In this case, in this case, we are doing work on the surroundings. We're doing 50 joules of work because we're pushing the balloon. The balloon's pushing air back. It's positive 50. So now we're going to do the formula. Hold on, there's a question. Let's do this formula. The formula is delta U equals Q minus W. That's going to be Q is 200 minus 50, which is going to be 200 minus positive 50 is going to be minus 50 equals 150 joules. That's how much our internal energy changed. But how it increases by 150 joules. That means that that will probably lead to the temperature of the balloon going up. Because remember, its internal energy is linked to temperature, so probably the temp increases. Now, it doesn't ask for that bit. I'm just putting that bit extra. Okay, we're going to do one more example here. I'm going to let you guys, I'm going to give you guys a minute to read that example, see if you can work out what the answer is on your own, and then we're going to do it together. Okay, first question. While doing some heavy lifting, you do 2,500 joules of work on the weights, while releasing 3,000 joules of heat. By how much did your internal energy change? Let's start with the start. Let's start with Q. Can someone tell me how much heat is getting transferred, and if it's positive or negative? Whoa, that's the big question here. In chat, I'd like to see the answer. Positive or negative, how much heat? Oh, good answer from some. Minvu said negative 5,000, negative 5,000. You are trying to get to the final answer straight away, I assume. But I want someone to tell me how much heat is being released. Just the heat, Q. What is Q going to be? Thomas has said negative 3,000. Elaine has said negative 2,500. So we've got 3 different answers so far. They're all negative. Anyone else got an answer? You can send it to me privately if you don't want me to read it out loud. And we said negative 3,000. And everyone's sending question marks because they're not confident on this, and I thought that might be the case. The answer is yes, negative 3,000. Why? Because it says while releasing 3,000 joules of heat. Now, if we're releasing it, that means we're losing that heat. That means it's going down. And if you think about it, if you're like working out in an air-conditioned room, you're going to be losing heat to your surroundings. In fact, we're all losing heat to our surroundings now, because our surroundings are, 25 degrees and our body temperatures internally is 37 degrees. We're all losing heat. Remember, I told you we're all emitting radiation. So that's something that we know is true. Next is W, work. Can I get someone to tell me how much work are we losing or gaining? Is it positive or negative? Are we doing work or is work being done on us? So I want you guys to tell me, what is W? We're doing work. Nurses, that's correct. So negative. You're so close. If we're doing the work, it's positive. Okay. Thomas saying 2,500. Nurse like, gotcha. Yeah. So we're doing the work, it's positive. Remember, the balloon was pushing against the atmosphere. That makes it positive. So Thomas was 2,500. Thomas, I'm going to question you if you give me the answer. Is it positive or negative? Positive 2,500 or negative 2,500? Beautiful, thank you. So yeah, 2,000, we do 2,500 works of the weights. That's positive 2,500. That's because we're pushing the weight up. Okay, we're releasing energy because we're pushing against the world. So that means if I then do this formula, delta U equals Q minus W, and I'm putting them in brackets because I want to do this properly. We've got negative 3,000 minus 2,500, positive 2,500, which is going to be negative 3,000 minus 2,500, which is going to give us negative 5,500. Negative 5,500 is our change in temperature, which means we're going to, the temp is going to decrease. So that's how you do these types of questions. Wrapping it up, we're going to call that the end of the lesson. Ladies and gents, if you need any help, if you need any assistance, please feel free to send me an email, and I'm more than willing to explain something that happened in that video, but you're more than welcome to just go backwards and rewatch certain sections. Anyway, I hope that helped, and I'll see you guys next time.